Hello, welcome in the 18th lecture of convective heat transfer. In our previous lectures, we have discussed about single phase convection. Here in this lecture, we will be actually describing the heat transfer with change of phase. Okay. So, our topic is heat transfer with phase change. Now, first let me tell you what things we will be covering in this lecture. We will be understanding phase change modes in context of convective heat transfer. What are the different phase change modes available where convection heat transfer is being observed. Okay. After that, we will be introducing boiling and condensation with its different modes. Okay. We will be also understanding what is the velocity and temperature profile in film condensation, and side by side we will be also discussing that what are the equations required for boiling cases. Okay. We will be evaluating condensate rate and profile of film accumulation over a surface, okay, over a cold surface, and then we will be understanding the governing equation for film boiling. As I have mentioned, apart from film condensation, we will be also learning film boiling situations. Okay. So, let me start. First, let me show you what are the effective convective modes involving phase change. As we are having convection, so definitely solid will not be coming into picture. We have to consider only the liquid and gaseous cases, and liquid and gaseous phase change processes are actually involved with two categories, condensation and boiling. Here I have shown a picture. You can see in this kettle the water is being boiled and it is forming some sort of vapor, water vapor, which is actually striking this bottom side of this plate. Over the plate we are having ice. Okay. So, here you can see this is actually forming vapor. So, liquid is actually forming vapor, and on the other hand you are having the ice. So, plate is having very low temperature. So, this vapor is immediately condensing, and here you can see the drop of liquid. So, in this plate the vapor is being converted to liquid. So, this is nothing but condensation, and here the liquid is being converted to vapor, and which is coming out from this kettle mouth. So, this is actually boiling. So, these two phases actually are involved with convective modes. So, that is why here in this lecture we are going to discuss about condensation and boiling. Okay. Melting, solidification and sublimation, those things we are not going to discuss over here, because those are related to solid, where convection mode is not that much observed. Okay. So, let me now tell that what are the characteristics of convection and condensation and boiling. So, for condensation we require cooling, whereas for boiling we require heating. So, here requires heating, here requires cooling. Okay. Next, droplet formation at low subcooling. So, for condensation you can find out at low subcooling. What is subcooling? If the temperature is lower than the saturation temperature, that is called subcooled condition, and the degree of lowerness is actually called subcooling. Okay. So, droplet formation we can observe at low subcooling, whereas in case of boiling bubble formation can be observed at low superheat. Okay. So, individual bubble and individual drop can be observed in cases of boiling and condensation respectively at low superheat and low subcooling. Next, liquid film formation at high subcooling we can see. If the subcooling is very high, we can find out if film of liquid is being formed over here due to condensation. In the same manner, in case of high superheat, gas film formation can be observed for boiling situations. Okay. So, what happens at high degree of subcooling or superheat, and what happens at low degree of subcooling and superheat, those things we have discussed over here. Next, let me start with the first mode, which is nothing but condensation. So, condensation is actually heat transfer to a surface. Heat transfer to a surface occurs by condensation when the surface temperature is less than the saturation temperature. So, this is very important. Surface temperature, let us say this is the surface temperature will be less than the saturation temperature. So, Ts is actually less than the saturation temperature. Okay. Saturation temperature of adjoining vapor. So, if we are having some vapor over here, so its corresponding pressures saturation temperature, that temperature will be higher compared to the surface temperature, then only condensation will happen. Okay. Next, as I have mentioned, we are having two modes of condensation where film is being produced and where particular droplets of liquid you can see. So, those are actually filmwise condensation and dropwise condensation. So, first let me discuss about filmwise condensation. So, film condensation is nothing but, in this case, entire surface is covered by condensate. So, if it is the surface, entire surface you can see is covered by this liquid condensate, okay, which flows continuously from the surface and provides a resistance to heat transfer between the vapor and the surface. As it is totally covered by the liquid, no fresh vapor can come in contact with the cold surface and further condensate. So, this gives a resistance. Okay. So, this liquid film actually gives a resistance to heat transfer. Okay. Next, thermal resistance is reduced through use of short vertical surfaces. To break this condensate, what you can do, small plates you can use. So, this single plate you can break into small plates, which will be breaking the liquid flow. So, thermal resistance is reduced through use of short vertical surfaces or horizontal surfaces. If you put horizontal surface, then obviously liquid will not be draining and you will find out resistance is actually being increases. Okay. So, resistance is increasing. Then characteristic of clean and uncontaminated surface. So, in case of clean and uncontaminated surface, dropwise condensation will be absent and we can find out majority of the surface is actually covered by film and we can have film condensation. Okay. Next, the other mode, so dropwise condensation. So, here surface is covered by drops in place of liquid film, whatever I have shown you in the previous slide. Here we are having, you see, liquid drops. Okay. So, surface is covered by drops ranging from few micrometer to agglomeration visible to the naked eye. So, very small droplets also can be seen, which are actually very small in the range of micrometers, and after agglomeration those micrometric droplets can become very big and even it can be visible with our naked eye. Okay. So, this type of thing you can see that these droplets are visible in the naked eye. Simultaneously, you can see very small droplets are over there at different places. Next, thermal resistance is greatly reduced due to absence of continuous film, as vapor can come directly in contact with the surface, okay, in this case in between the droplets. So, resistance is greatly reduced. Okay. Then surface coating may be applied to inhibit wetting and simulate droplet condensation. So, what you can do over the surface, if you apply special type of coating, then you can find out that film wise condensation is actually discontinued and it will be forming some sort of dropwise condensation like this if you play with the wettability. Okay. Then steam condensation on copper surface, if you see, then that can be written in this fashion: Q is equals to heat transfer coefficient of dropwise condensation into area of the surface at which the condensation is happening, minus of Tsat minus Ts. Ts is the surface temperature, Tsat is nothing but the saturation temperature for the vapor at that given pressure. Okay. So, this HDC is nothing but the heat transfer coefficient for the dropwise condensation. There are several correlations for finding out this heat transfer coefficient. I will tell you one correlation. So, HDC can be written as 51100 plus 2044 into saturation temperature, okay, if saturation temperature lies in between 22 degree to 100 degree. Okay. And if the saturation temperature is more than 100 degree, then simply you can write down HDC is equals to 255500. Okay. So, this type of correlations people use to find out the heat transfer coefficient for droplet condensation and ultimately obtain what is the heat flux for a situation where droplet condensation is happening. Okay. Next, let me show you what are the stages in droplet evaluation. So, process involved in droplet condensations are initial nucleation of drop on previously bare surface. So, initial nucleation, small nucleation sites you can see. Then you can find out growth of drop. These drops will be becoming bigger by growth. So, you see all these nucleation site has actually grown up. And then you will be finding out coalescence of drops. So, now you see if they grow further, then these two drops will be coalescing over here and form coalesced drop over here. So, coalescence of droplet which grow large enough to touch each other. So, here they are touching each other. Then we will be having additional nucleation of new drops. So, apart from these coalesced drops, there can be some additional nucleation also like this, okay, additional nucleation of new drops in areas which become available due to coalescence. So, after coalescence some area will be vacant. So, there we can have new nucleations also, and side by side we can have loss of drop due to gravity if the surface is having inclination with horizontal. So, that I have not shown over here. The droplet which is becoming bigger in size, that can dislodge from the surface if the surface is having inclination with the horizontal. Okay. So, by virtue of gravity that can fall down. So, all these are actually stages of your droplet condensation. Next, let us move back to the film condensation, Filmwise condensation, and let us consider that now we will be having a vertical plate. So, situation will be changing if the plate is having inclination with the horizontal. Okay. So, it is actually a perfect vertical plane having 90-degree inclination with the horizontal. So, in this case what are the distinguished feature we can see? Let us say this is the plate having temperature Ts, okay, which is lower compared to the saturation temperature of the vapor T infinity. Okay. Saturation temperature of the vapor is T, let us say T saturation is the saturation temperature of the vapor. Then you can find out that whenever the vapor is coming in contact with the surface, there will be condensation, immediate condensation will be there. So, the temperature profile will be actually increasing in this fashion as Ts requires to be smaller compared to the vapor temperature for necessary condensation. So, this way the temperature profile will be reducing, lower at the plate and higher at the vapor. Okay. And as we are having film over here, so this film due to the verticalness of the plate, the film will try to fall down by virtue of gravity. So, you will find out there is a flow also incurring in this. So, the velocity can be velocity profile can be shown like that. Due to no slip, it will be having 0 velocity adjacent to the wall, and far away from the wall where there is no film, obviously the velocity will become 0. Okay. At the interface, so you can see a parabolic film like this will be generated because film is draining from the top, it will be accumulated at the bottomward side. So, you will be finding out thicker film at the bottom and thin film at the top. So, near the film you will be finding out there is continuity between the liquid velocity and the gas velocity. Okay. So, it is very important to find out this thickness of the film, which will be depending on the plate direction, which is x direction over here. So, delta is actually a function of x. So, it is very important to find out the thickness delta as a function of x, as well as what is the film drainage rate. Okay. So, flow rate of the condensate, because it will be draining with respect to time. So, we have to find out the flow rate. Okay. Next, generally the vapor is superheated and may be part of mixture that includes non-condensable. So, it can have that vapor is having mixture with some non-condensable material also, which will not be condensing whenever it is touching this surface. Let us say that part that material is having saturation temperature lower than this surface temperature. So, that will be acting as non-condensable gas. Okay. So, generally the vapor will be superheated having higher temperature compared to saturation temperature, and may be part of mixture that includes non-condensable. A shear stress at the liquid vapor interface includes a velocity gradient in vapor as well as liquid. So, if you find out at the interface there is some sort of velocity gradient in the liquid side as well as in the gas side. Okay. So, those also we need to consider in case of film condensation. So, let me first try to form the governing equations. So, at x equals to 0, that means at the leading edge you can consider that the pressure is nothing but your vapor pressure. Okay. So, PV naught, okay, because there is no film, okay, and or we can say there the film is being initiated. Okay. And we can also see over there all velocities are 0, okay, because there is no film at all, and temperature is nothing but your vapor temperature T infinity. Okay. So, Tv is T infinity. So, at x equals to 0 we can get pressure, all velocities and temperature as there is no film at the leading edge. Okay. Then if you see the equations over there, so we will be finding out that from there the drainage starts. So, we can write down del x of P v is equals to rho v into g. So, this comes out from the momentum equation at the leading edge. Okay. So, here if you equate, by the way, this P equals to PV we have used over here. Now, if you integrate this one, then you will be finding out PV is equals to some constant. Now, if you apply this boundary condition, that constant will become PV naught plus rho V into G into X. Okay. Now, if you take PV naught common, it becomes 1 plus rho V G into X by PV naught. Now, near the leading edge, X is very small. So, what we can do? We can neglect this part and we can write down PV is equals to PV naught near the leading edge. Okay. And as a result, the saturation temperature which is actually a function of vapor pressure. So, PV saturation temperature is a function of vapor pressure, and just now we have showed this is nothing but vapor pressure at the leading edge PV naught. Okay. So, the saturation temperature actually becomes a function of PV naught at the which is at the pressure at the leading edge. Okay. So, we have got some idea of T sat which will be a function of PV naught. Okay. Next, let us try to find out what happens at the liquid film. So, first let me show you, let us say this is the plate, vertical plate, and here we are having the film. Okay, parabolic film, let us say it is forming like this, thicker at the bottom side and thinner at the top side. Now, let us take a small strip around the interface where in the left hand side we are having liquid and right hand side we are having gas. Okay. So, if you do so, first let us try to do the mass balance. So, if you find out the mass balance, so m dot, okay, will be actually rho a v n. So, perpendicular directional velocity v n of this strip. So, rho a v n into L. So, this will be liquid will be entering through this lengthy section, okay, and then is equals to rho a v n of V. So, in the vapor section. So, for this small strip, if you do the mass balance, considering that this is very lengthy film in the other direction. So, these two surfaces we are actually neglecting. So, we are having m dot is equals to rho a v n L is equals to rho a v n V. Okay. Remember, this v n is nothing but V into n cap. N cap is the perpendicular direction of the surface. Okay. So, tiny surface whatever we have taken. So, if we take this mass flow rate and then let us go for the energy balance. If we go for the energy balance, then we can find out that whatever we are getting from this side, so which is nothing but m dot mass flow rate into H L plus V L square by 2. So, H L is nothing but the enthalpy of the liquid side, V L is the velocity of the liquid which is entering in the domain, okay, by 2 is equals to m dot, same mass flow rate, obviously this we are same. So, that is why we have taken both side m dot into H V, which is the enthalpy of the vapor side, plus V V square by 2, V V is nothing but your vapor velocity. Okay. On the other hand side, we are writing Q dot, which is the heat transfer occurring in this small strip, minus of W dot, which is nothing but work transfer. Okay. So, coming from our first law of thermodynamics. Okay. Now, you see here W naught will be obviously 0 because there is no feasible work done over here. So, W naught let us put 0, and for the Q naught there will be conduction, okay, because this is a very small strip, convection cells will not be there. So, this is conduction. So, if you go for the conduction, then you can find out Q dot is equals to minus K del T del N A for the liquid side is equals to that. That means, here as this strip is across the interface, some part will be for the liquid, some part will be for the gas. So, this is the conduction in the liquid side and this is the conduction in the vapor side. Okay. Now, if you see actually this Kv thermal conductivity of vapor is very small compared to Kl. So, if you incorporate this, then we find out Q dot is nothing but minus K del T del N A for the liquid side. So, conduction in the vapor side can be neglected in comparison to the conduction of the liquid side. Okay. So, let us consider Q dot is equals to this term, conduction in the liquid side only. So, if you put this over here in this equation and W naught equals to 0, so we get this equation rho a V n cap at the interface. Okay. So, let us consider that this mass m dot is nothing but this at the interface, okay, rho a V n cap, V n is nothing but V n cap, okay, then H f plus V L square by 2, okay, is equals to once again that same m dot over here, okay. same m dot into Hg plus Vg square by 2, and in case of q dot we have written only the conduction for the liquid side. Okay. So, with this here you see the left hand these two terms we can actually simplify, considering VL and VG they are very small compared to the enthalpies, and HF minus Hg can be written as HFG. Okay. So, ultimately we get the energy equation across this strip is equals to K del T del N at interface is equals to rho V n cap interface into HFG. Okay. So, we have taken several assumptions over here. Please remember Kv is less than Kl, and here we have considered the velocity head is very small. Okay. So, this we got as our energy equation. So, let me show you now the equations for the volume liquid film. So, this is the continuity equation del u del x plus del v del y equals to 0. Then we are having the x momentum equation like this, okay, where we will be having the buoyancy term over here rho into g. Y momentum equation is del p del y equals to 0, and then subsequently from here we get del p del x is equals to minus del p v del x is equals to rho v into g. Okay. And then subsequently energy equation is in the left hand side we are having convection, right hand side we are having the conduction. Okay. So, this is the falling film analysis, but let us now do some simplification of all these equations so that we can solve, and in order to do so let us take Nusselt's analysis. Famous scientist Nusselt, he has derived this analysis. What he is proposing? He is proposing let us take this film as laminar, let us take this film as steady. So, all temporal term we can actually neglect, and then we are having constant properties. So, all the properties like rho k can come out. Okay, and then negligible streamwise diffusion in the momentum term. So, in this momentum term if you see we are having streamwise and cross streamwise diffusion. So, streamwise term we will be cancelling. Similarly, we are having negligible streamwise diffusion of heat. So, in the conduction term we can also neglect the streamwise diffusion. Negligible inertia and convection. So, inertial side and convection side totally we can neglect. Okay. So, with these assumptions which has been proposed by Nusselt, we are actually reducing our momentum equation and energy equation in this form. So, you see all the del square del x square term has been cancelled from the momentum equation, inertia term has been cancelled, steadiness to obtain steadiness del del t term has been cancelled, same thing has been done from this side also. Okay. So, all del square del x square term has been cancelled and convection term has been cancelled. Okay. Now, if you try to solve this equation using these boundary conditions at y equals to 0, that means at the plate you will be having velocity equals to 0 and T equals to wall temperature, which is nothing but Ts. Okay. And at y equals to delta, that means at the boundary layer. Okay. So, here at the film edge if you write down, then there we will be having del u del x equals to 0. Here you can see velocity exists, but the gradient of velocity we can say at the film edge is 0. So, del u del y is equals to 0 and T becomes saturation temperature, because this is the end of the film. Okay. So, if we take these boundary conditions, first let us take the momentum equation to solve this momentum equation. So, this was my reduced momentum equation from here using Nusselt analysis. So, that momentum equation if you integrate and energy equation is like this. So, if we integrate these two equations, we get first the u pattern from after integrating of this one like this, and using these two boundary conditions obviously we get the liquid film velocity as this. Very simple integration we are having and finally we will be getting this type of equation. Okay. Here you can see this u is actually a parabolic function of y. So, that is why we have got this type of equation, this type of velocity profile. Okay. And on the other hand side, temperature profile using these two temperature boundary conditions and this equation, we get T sat minus T by T sat minus T w is equals to 1 minus y by delta. Okay. So, it will be short of linear profile. So, we have shown like that, okay, continuously increasing linear profile. Okay. So, we have got the liquid film velocity profile and temperature profile for the condensate in this fashion. Next, let us try to see what is the mass flow rate through this liquid film. Okay. So, mass flow rate m dot already we have seen that will become rho u dy and the limit will be from 0 to delta. So, as we have already obtained the profile for u, so let us put that one over here, and this is now becoming a simple integration with respect to y, and if you proceed further, then we will be getting m dot is equals to rho into rho minus rho v into g by mu into delta cube by 3. Okay. Once you put the upper limit and lower limit. Okay. Then if you go for the energy balance, this equation already we have derived by taking a small strip around the film. If you remember, for some infinitesimal small strip, we can write down m dot is equals to dm. So, this was the equation. Here you see, if this strip is very thin, then we can write down dA is equals to dx, okay, because in the y direction the strip thickness will be very small. So, once you have this equation, then from here we can write down del t del n is nothing but del t del y, because in x direction there is we are considering that there is no gradient, because that is almost a vertical strip. Okay. So, here from we can write down this is nothing but delta t by delta. Okay. So, if we put all these things over here, then we get del m dot by del x is equals to this fashion. Okay. So, here you see once again we have got some differential equation which we can integrate. So, let us try to integrate with respect to x. Before that, let us put the value of del m del x over here using this equation. So, once you put this del m del x using this equation, it becomes k del t delta by delta into dx is equals to rho minus rho v into g by mu into delta square d delta into hfg, okay, which can be now easily integrated. Once you integrate, then you will be finding out and put the limit from 0 to x. You will be finding out that this becomes delta to the power 4 by 4 is equals to mu k delta t by rho into rho minus rho v into g into hfg into x plus a. Okay. And evaluation of a is very easy, as x equals to 0, delta equals to 0. So, a will be becoming 0. So, finally, we get delta in the form of 4 mu k delta t by rho into rho minus rho v into g hfg into x to the power 1 by 4. Let us try to reduce this by finding out some non-dimensional number over here. So, here you see we have clubbed it into two parts, okay, and both this part is actually giving me, this is giving me actually Rayleigh number. So, 4 by Rayleigh number. So, rho del rho g x cube by nu a. So, that is giving me Rayleigh number, and here this is nothing but Jacob number. So, this is giving me delta by x is equals to 4 by Rayleigh number into Jacob number to the power 1 by 4. So, ultimately we can write down this film Rayleigh number is nothing but Rayleigh number by Jacob number. So, this becomes delta by x is equals to 4 by film Rayleigh number to the power 1 by 4. Okay. Next, let us move to the other portion after this evaluation of the boundary layer in the condensation side. Let us move to the boiling side. So, in case of boiling, we know that it will be actually the process in which addition of heat, in this case it will be addition of heat to a liquid generates vapor. Okay. So, just the opposite of condensation. So, in this case boiling are having actually two modes, pool boiling. So, it is nothing but on a pool you will be having some hot surface somewhere, from there the boiling will be appearing. Okay. And another one is flow boiling, where there will be predominant motion of liquid and it will be actually having boiling due to heating around. Okay. So, here we are having predominant motion, here there is no dominant motion, but the motion will be generated due to the convection currents. Okay. So, key distinctions, as I have already mentioned, natural convection actually takes part in this pool boiling. Okay. And in case of flow boiling, this actually fluid is moved across the surface and heat transfer is driven by the flow. So, this we can say this is forced convection driven and this is natural convection driven. Okay. Next, this is very elemental. Let us try to show different boiling zones. So, at the beginning we will be having actually natural convection, where the temperature will be rising up to the saturation temperature from atmospheric temperature. This is actually boiling curve in between the heat flux and degree of superheat delta T, wall temperature minus saturated temperature. Wall temperature is higher compared to saturation temperature in this case for boiling. Okay. And after that we will be having a zone where we will be having small bubble formation, which is nothing but at low superheat, and it is called actually nucleate boiling. Okay. Then after that there will be a sudden jump, okay, in temperature in case of your heat flux controlled experiment, and you will find out that this zone is nothing but transition boiling, and after this suddenly you will be finding out the whole surface is actually occupied by a liquid film, which is a gaseous film, which is nothing but actually film boiling region. Okay. And if you just reverse, it will be actually jumping from lowest point, which is nothing but the leaden frost point. Okay. So, if you lower that this one temperature or lower the heat flux, so this will come like this, and then it will jump to the nucleate boiling region and subsequently go for the natural convection. So, let me show you different modes. So, in the natural convection zone, you can find out no bubble is involved. So, only the natural convection is actually predominant, okay, over a horizontal surface. Here in nucleate boiling zone, small bubbles you can see. So, in this zone, small bubbles you can see. At transition, these bubbles will be merging vertically as well as horizontally. Okay. So, transitions, and then it was merging actually vertically, and here I have shown the merging in the horizontal direction also, and this will be becoming bigger and bigger in size to occupy the whole surface, okay, and ultimately you will be having a film over the surface. Okay. So, in this region we will be having a film over the surface, right. So, these are different boiling zones we are having. Now, let me show you the equation for film boiling. This situation is just the opposite of the film condensation. So, this is the surface which is having temperature higher than the saturation temperature of the liquid, surrounding liquid. So, here you can see you will be having vapor formation when the liquid comes in contact with the surface, there will be vapor formation, but the vapor by virtue of buoyancy will try to move up. Okay. So, as a result you can find out that in the upper side the vapor film thickness is higher compared to the lower side, just opposite of the condensation. Okay. So, the equations and corresponding boundary conditions, subsequently the solution methodology will be also similar. So, let me show you the equations quickly. So, these are the momentum equations. So, pressure will become PV as we have shown in case of condensation also, and mu is equals to mu V, okay, because here vapor is being attached with the surface. So, for the liquid we can get, these are the equations, this is the governing equation, and regarding velocity we can say UL and VL is equals to 0, there will be at no velocity in the liquid domain. Okay. So, we can get PL in this fashion, PL naught minus rho L into G into X, its derivative will become minus rho L into G. Okay. And its momentum equation, now its energy, its momentum equation will be something like this, where del P del X minus rho G term we have actually converted into this one. Okay. So, del P del X actually we have found out minus rho L into G. So, if you plug it over there, so this will be becoming rho L minus rho into G. Okay. And then this will be the at the interface, this will be the stress boundary condition. So, at y equals to delta x, mu v into del y del u del y at vapor region, the stress, shear stress in the vapor region is equals to shear stress in the liquid region. So, this will be the boundary condition at the film edge, okay, gaseous film edge. So, with this we can solve similar way this equation and get film thickness for film boiling situation. Okay. So, with this let me end this lecture. So, in this lecture we have described the basic difference between boiling and condensation along with its different mode. We have discussed the mechanism of droplet growth, shrinkage during condensation on a surface. We have balanced mass, momentum and energy equation around a film during condensation. We have predicted liquid film accumulation rate along with its profile along the vertical surface, and finally, we have described the governing equations for film boiling situation in a vertical surface. Okay. Let me test your understanding at the end of this lecture. So, we are having 3 questions once again. First question goes like this: necessary condition for condensation. We are having 4 conditions. TW wall temperature is less than the saturation temperature, wall temperature is higher than the saturation temperature, wall temperature need to be 0 Kelvin, and wall temperature is equals to triple point. It is very simple one. So, the answer is nothing but A, TW less than T saturation, then only the condensation will occur. Okay. This is for the boiling situation. Necessary assumptions for the Nusselt number, we need to give the necessary assumption for the Nusselt number in second question. We are having 4 options: laminar, neglect the inertia and convection, neglect buoyancy, and neglect crosswise diffusion of momentum. So, this momentum will come here. So, neglect crosswise diffusion of momentum. Okay. So, all actually you can see from the assumptions whatever I have mentioned in this lecture, that for Nusselt analysis we need to be laminar definitely, and inertia and convection needs to be neglected. Okay. Last question is, condensate rate is proportional to 1 by delta, delta square, delta and m delta cube. So, condensate rate means m dot. So, m dot is proportional to this, also we have derived. So, obviously the correct answer is delta cube. Okay. So, I believe all of you have got the correct answers for all these 3 questions. So, with this we will be ending this lecture. In our next lecture we will be discussing about mass transfer. Okay. So, if you have any query about this lecture, please keep on posting in our discussion forum. Thank you.